Hi guys, my name is Jasmin Gonzales and I'm going to continue the discussion of our topic, the falling head permeability test. So let's continue. Now, if we have a manometer at the bottom of the sample and when water flows through the soil, the water level in the manometer will display the exit head of the water. But if we place the instrument in a tub-like container full of water, its exit head will become constant. Also, if we consider the exit head or water level of the container as datum, then datum head is 0. So exit head is also 0. And initial inlet head of the water in the standpipe from datum is say H1. Hydraulic gradient, which is the difference of the inlet and outlet head divided by the length of the soil specimen in which the flow takes place, will only depend on the height of the water column in the standpipe as outlet head is 0. When we open the outlet knob, water comes out and overflow the container. We start a stopwatch and place a graduated jar to collect that overflow water. We collect the water for a fixed time interval T and note down the amount of water collected as capital letter Q. We close the knob and also note down the final head in the standpipe, which is also the final head difference from the datum. We call it H2. Keep in mind that H1 and H2 are the heights of the water column in the standpipe and also the head differences which are causing the flow. Now, for this system, we may apply Darcy's law which states that the velocity of flow of liquid between 2 points in the soil is directly proportional to the hydraulic gradient applied to it. And K is added as proportionality constant, which is called the coefficient of permeability of soil. We also write the law of discharge rate as this. We can notice that hydraulic gradient through the soil is changing every instant as the water head is continuously changing in the standpipe. So let at any instant of time when the water head was in between H1 and H2, the head difference which was causing the flow through the soil is H. For a very short interval of time, dt, head in the standpipe, drops by dh height. At that instant, when the head is h, the flow rate can be given as this, and the amount of water collected in the jar was this rate in small time interval, dt will be q times dt. So using the continuity equation, we can write volume of water dropped or decreased, negative sign for the decrease, in the standpipe is equal to the discharge of water collected or increase in the jar through the outlet. Volume of water dropped in the standpipe is area of standpipe multiplied by the height of drop of water, and the amount of water collected in a jar is discharge rate multiplied by time interval. We can write discharge rate by Darcy's law as this. Hydraulic gradient I for that instant of time was h over L. Then we can rearrange it and write it as this. Here, some values are constant and for our taken test conditions, permeability is constant. Only variables here are head difference and time. So we can integrate both from head difference at initial head difference of H1 at time t equal to 0 to the final head difference of H2 at time t equal to t. Now, we can integrate and apply the limits. Also, we can rearrange to find the value of permeability as this. Here, log has its base e that can also be written as this for base 10. In this equation, we have measured and recorded all the required values to calculate and know the permeability of the soil sample. According to the Indian standards, we report the permeability values at 27 degrees Celsius temperature. So if we measure the temperature of the water as T degrees Celsius, then using this formula, we can calculate the permeability at 27 degrees Celsius. Here, K27 and KT are the permeability of the soil at 27 degrees Celsius and at the test temperature T degrees Celsius respectively. Mu27 and mu-T are the coefficient of viscosity at temperature 27 degrees Celsius and test temperature T degrees Celsius respectively. So my partner and I prepared a sample problems for you. Example number 1. For a falling head permeability test, the following values are given. Length of specimen is equal to 200 mm. Area of soil specimen is equal to 1000 mm squared. Area of standpipe is equal to 40 mm squared. At time t is equal to 0, the head difference is 500 mm. At time t is equal to 180 seconds, the head difference is 300 mm. Determine the hydraulic conductivity of the soil in centimeter per second. So we are going to use the formula K is equal to 2.303 times small letter a times L over capital letter A times T, then log 10 times H1 over H2. Then plug the values in and we get 2.27 times 10 raised to negative 2 mm per second. So we're going to convert that into centimeter per second. So we can get that just by dividing it by 100. Then we get 2.27 times 10 raised to negative 3 centimeter per second as our final answer.
For our next problem, for a falling head permeability test, the following values are given. The length of specimen is equal to 8 inch. The area of soil specimen is equal to 1.6 inch squared. The area of standpipe is equal to 0.06 inch squared. The head difference at time t is equal to 0, which is equivalent to 20 inch. The head difference at time t, 180 seconds, is equivalent to 12 inch. So determine the hydraulic conductivity of the soil in inches per second. So for our solution, we have the given following values and we will solve it by using the falling head permeability test, where the K is the coefficient of permeability is equals to 2.303 times A, which is the area of the standpipe, multiplied by the length of the specimen, all over A, capital letter A, which is the area of the soil specimen, multiplied by the time, log, and the quantity of H sub 1, which is the initial head difference at time t, all over final head difference at time t, which is the H sub 2. So substitute the given values in the formula. So we have K is equals to 2.303. The A is 0.06 divided by the A length over 1.6 versus 180 seconds. Log 10 and H sub 1, which is 20 over the 12 inch. Our K will be solved in a calculator. 2.303, 0.06 divided by 8, 1.6 multiplied by 186 then log the head sub 1, H sub 1, which is 20 over 12. So the answer is 8.52 times 10 raised to the power of negative 4 in inches per second. So this is the answer in determining the hydraulic conductivity of soil in inches per seconds.
That's all, guys. Thank you and God bless.